Hi, everyone. Thank you for joining us for today's webinar on operating room air distribution. We're planning on about 45 to 50 minutes of content, followed by 10 to 15 minutes of Q&A. Before we begin, we have a few housekeeping items to cover. So if you mouse over the bottom part of the screen, there's a Q&A icon. Feel free to ask your questions in that area. Anytime during the presentation, we will go ahead and answer them at the end. There is also a chat window where you can ask questions or talk directly to us. So once we begin, if you happen to have any audio or video issues, this is where you would want to communicate them to us. Finally, for those that require continuing education credits, we will have a link to the quiz at the end of the presentation. We will share that in the chat window and email it out to those that have requested credit in the registration form. Once all has been verified and approved, we will email you your certificate. So with that, I'd like to go ahead and turn it over to Neil Holden, our Specialty Product Manager. Neil, take it away.
Thanks, Lily. Good day, everybody. I'm Neil Holden. I'm the Specialty Product Manager at Krueger, and today we're going to be discussing operating room air distribution. So let's just jump right into it. Our agenda for today is we're going to go over some basic goals for operating room air distribution, discuss key design considerations for operating room air distribution, as well as air distribution design standards for the operating room as serviced by FGI and ASHRAE 170. Then we will discuss operating room air distribution design using non-aspirating laminar flow diffusers, as well as with an air curtain. Then we'll wrap everything up with a quick summary before finishing off with some OR room design examples. So the general guidelines for our general goals for operating room air distribution are, number one, first and foremost, we want to provide patient safety. We want to reduce the risk of surgical site infection. To do this, we have to create an envelope of clean air around the staff and the patient. Now, the patient is the obvious target, but the staff standing around the operating room table, they also need coverage. Our devices in the space need to be able to control the velocity and temperature of air at the patient, and we need to exhaust and reduce risk of particulates to re-enter the surgical space. Surgical site infection prevention is a high priority goal for healthcare organizations. As you can see from these two quotes, according to data from the AHRQ, more than 10 million patients undergo surgical procedures as inpatients each year. Surgical site infections occur in 2% to 4% of all patients undergoing inpatient surgical procedures. So if we do the math real quick, out of 10 million patients, that means we're having about 200,000 to 400,000 patients affected by surgical site infection. And then approximately 3% of those affected patients who contract an SSI will die as a consequence. So that's over 6,000 deaths per year due to SSI. So you can see why SSIs are extreme high priority to reduce for healthcare organizations. Another fact is that SSIs also increase the cost of care for the hospital. They calculated this cost, it could be as approximately $30,000 in additional index stay cost per harm. So hospitals have multiple reasons, to reduce surgical site infections, mainly for the comfort and well-being of the patient, but also because it increased their operating costs. So let's discuss some design considerations. Some of the key considerations for HVAC air distribution systems are they're required to play many different roles and unique roles in critical environment spaces. Operating rooms are obviously critical spaces. We want to make sure we have clean air and a clean environment. Pressure control varies by space type as well. For example, OR rooms generally require positive pressure, while labs generally require negative pressure. In an OR room, positive pressure will prevent contaminants from entering the space into the operating room. Because we do have occupants in the space, we do need to get some supply air ventilation into the space as well. The standard also identifies filtration requirements for contaminant removal. And these are indoor spaces, so temperature and humidity control will be important as well. Finally, air devices selected for an operating room should be suitable for withstanding regular cleanings and wipe downs. We want to make sure the diffusers are accessible and cleanable, providing access to the plenum as needed for regular cleaning. Airborne contamination control is the number one concern for these spaces. We do have to be aware of some sources of contaminants. It could be coming from the ventilation. We have a combination of outdoor air and return airs flowing through an air handler, various coils, and ductwork before it enters the space through the diffusers. Potentially, the air could pick up some contaminants along the way before it enters the space. Pressurization is key in preventing contaminants from entering the space. Positive pressure prevents airborne contaminants from flowing underneath doors or through small openings, infiltrating the space and adding to the airborne contaminants. The number one source for airborne contaminants in the space is actually from the patient and the surgical team itself, or the occupants of that space. The skin cells that come off the human body are the number one source of particles as well as pathogens in the OR space. So now let's jump into some of the standards. There were actually very few hospitals built during the periods between the two world wars, resulting in a severe shortage after World War II. The Hill-Burton Act of 1946 granted federal funds for hospital construction. This was accompanied with general standards for hospital construction and equipment, giving the U.S. a federal standard. This standard was maintained by the Public Health Services Committee, which eventually transitioned to the American Institute of Architects, or AIA, which took over and published the standard from 1987 to 1998. In 1998, the standard was turned over to the Federal Guidelines Institute, FGI, which published 2002 and 2006 editions under the AIA name. Finally, in 2010, they published the first standard under the FGI name. In 2014, they split the standard into two standards, one for hospitals and outpatient care, while the other standard was for residential care. And then in 2019, they split it into an additional standard for a total of three: hospital care, outpatient care, and residential care. Now, having said all that, luckily, FGI incorporated ASHRAE 170 standard in 2010. So ASHRAE 170 is now the one standard that the industry has rallied around. ASHRAE 170 was first published in 2008. The current edition is ASHRAE 170-2017. Since ASHRAE has been incorporated into the FGI guidelines, it really is the one standard that you need to be most familiar with. The FGI just mirrors the ASHRAE 170 standard. The ASHRAE 170 is due for the next publication to be later this year. So if that were to come out later this year, the most recent standard would then go to 170-2019. So some of the standard 170 requirements that ASHRAE provides are the first design requirements we want to look at is the proper diffuser selection and placement. In the table above, ASHRAE 170 requires supply diffusers placed within the primary supply diffuser array to be non-aspirating. That term, non-aspirating, can be described in other ways. For example, non-aspirating is also referred to as laminar, non-mixing, or one-directional flow. ASHRAE 170 defines the primary supply diffuser array as the area that extends 12 inches outwards from the OR surgical table. So we will continually refer to this term, the primary supply diffuser array, continuing in this presentation. Laminar flow diffusers, defined by ASHRAE 170 as non-aspirating diffusers, are designed to be used in an OR above the surgery table and staff to provide a sterile field during surgery. The reduced effective area of the diffuser face is used to create a nominal airstream velocity averaging 25 to 35 feet per minute. The airstream provides a clean piston of air with minimal entrainment to create a sterile field around the surgical table. And so you can see through the illustration, laminar flow is a smooth one-directional flow, as you can see with these arrows designating, versus turbulent or mixing. This is what traditional overhead mixing is accomplishing in the space. This is not ideal for use over a surgical table because you can't guarantee that you can keep out entrainment of particles and pathogens in the space. Two key requirements for ASHRAE 170 compliance include nominal air discharge velocity and diffuser coverage over the OR table. In regard to air velocity, we must use a laminar flow diffuser that provides 25 to 35 CFM per square foot of laminar face. Average velocity needs to fall between the 25 to 35 feet per minute. Average velocity is also referred to as nominal velocity of the diffuser. To determine nominal velocity, ASHRAE 170 instructs us to take the total CFM supplied to the diffuser and divide by the nominal face area of the diffuser. For example, a laminar diffuser handling 240 CFM that measures 2 by 4 on the face will provide about 30 feet per minute nominal velocity. 240 divided by 8 equals 30. In addition to the air velocity requirement, ASHRAE 170 dictates that at least 70% of the primary supply diffuser array consists of diffusers. Again, the primary supply diffuser array is that area that extends 12 inches from each side of the surgical table. So of that area, at least 70% would need to provide air distribution. The remaining 30% can be made up of non-diffusers, such as lights, surgical booms, access panels, etc. The general size of a surgical table is about 6 foot by 2 foot. So most primary supply diffuser arrays will measure 8 foot by 4 foot at minimum. We want to make sure the air entering the OR space is clean and uncontaminated, so filtering the supply air is a key requirement in ASHRAE 170. ASHRAE 170 provides filter standards for filter banks located at Bank 1, which is defined as being upstream of the coils. This filter bank needs to be MERV 7 or better. Bank 2, however, is located downstream of the fan, wet coils, and all other mechanical components within the air handler. For most practical purposes, Bank 2 is commonly located at the diffusers in the primary diffuser array. So for this instructional period today, Bank 2 will be located directly within our non-aspirating laminar diffusers. Filter Bank 2 are the laminar diffusers located in the primary diffuser array directly above the surgical table. As you can see in the chart above, ASHRAE 170 requires a minimum filter efficiency of 14 in Bank 2. However, many times you will see this MERV rating upgraded to HEPA filters. HEPA filters meet a MERV rating range of 17 to 20, so they exceed the minimum 14 MERV requirement. HEPA filters also remove at least 99.97% of particulates sized 0.3 microns or larger. For today's discussion, we are focusing solely on operating room design. As you can see, some of the key requirements for operating rooms at the bottom of the above chart. A total of 20 air changes per hour are required, where 4 minimum air changes per hour come from outdoor fresh air. Also, a positive pressure relationship of at least 0.01 inches water column must be maintained to adjacent spaces. The relative humidity for the room should fall between 20% to 60% relative humidity. You actually don't want your operating space to be too dry, because a dry climate actually allows particulates to move around the space more easily. Also, the target ambient temperature for the operating room should be between 68 to 75 degrees Fahrenheit, but this can vary based on surgeons' personal preference. Many surgeons prefer ambient room temperature several degrees below the ASHRAE target range. Now we will begin to discuss operating room design based on laminar flow design. The image you see here shows an ideal true one-pass system. In this case, your supply would be above the OR table and your exhaust would be built directly into the floor. This would be accomplished via a raised floor, similar to what you would see in some computer rooms. However, this is not conducive in the operating space due to the strict cleaning regimen the space is subjected to. Having a raised floor would just be a breeding ground for too many pathogens and really make it difficult to eliminate this, one of the key sources of contaminants in the space. So in reality, what we really see is this illustration shown here. We see the supply above the OR space, and the exhaust is located at low sidewall grills. And so in this image, we can see the return grills located on this back wall behind the equipment. And we have laminar flow diffusers that are located above the OR table, blowing straight down, providing a curtain coverage around the patient and also any staff that's standing directly next to the table. Here we see a top-down plan view of a typical operating room that has the surgical table designated And then we are extending the primary diffuser array 12 inches to each side of the table. And you can see that 12-inch extension in the shaded blue area. ASHRAE defines the area that extends 12 inches for each side of the surgical table as the primary diffuser array. Typical tables measure about 2 foot by 6 foot. So in this case, 70% of this blue area in the ceiling would need to consist of laminar flow diffusers. So if we take that a step further, here we are actually placing our laminar flow diffusers, which are 2x4 diffusers in this case, and we have mapped out 70% coverage as indicated by the 3 2x4 laminar flow diffusers. This maximizes coverage over the patient, will provide 25 to 35 CFM per square foot of laminar diffuser. So if we do the quick math on that, basically we have 3 2x4s, so that's 8 square feet each, so we have 24 square feet. So we have 24 square foot of diffuser at 30 CFM per square foot. That provides a total of 720 CFM through those 3 laminar diffusers. However, we have more room air that we have to make up to achieve the 20 air changes required for the space. So we're going to have to add some additional laminar flow diffusers. These laminar flow diffusers can be located directly to maximize coverage over the patient and the surgical staff. And again, we've added 4 laminar flow diffusers. Each one is 8 square feet. So we have 32 square feet at 30 CFM per square foot equals an additional 960 CFM. So our total CFM for the space through the laminars now is 1680. So the goal of the laminar diffuser is to create a clean air envelope. So this envelope is designated as this light blue shading covering the OR table in the image above. The OR table is designated with the dashed lines, and then we take this dashed line, extend outwards by 12 inches on all 4 sides, and that will provide the area that we need to provide laminar coverage. The goal of the laminar diffuser is to provide a discharge supply with a velocity ranging from 25 to 35 feet per minute at the table. This reduces risk of particulate reentry by creating a smooth piston of air that surrounds the patient and the staff, eliminating and restricting the entrainment of airborne particulates from coming into that clean piston of air. Return grills should be located near the floor, approximately 8 inches above the floor, with a minimum of 2 grills in each room. ASHRAE 170 tells us that we have to have a minimum of 2 low-level exhaust grills. 4 is preferable, but to be ASHRAE compliant, you only need 2. The return grill should be mounted 8 inches above the floor, in the center of a wall, or in the corner of the room. You should size the exhaust grills to handle 500 feet per minute in return. And that's a general recommendation for sizing the return grills. Now, one of the problems with handling the primary diffuser array with just pure laminars over the OR table is something that we're going to discuss next and was highlighted in an ASHRAE research project 1397. So some of the challenges for an all-laminar flow design include airfield collapse. And that's what we're seeing in this illustration above. So this is a CFD computer analysis that simulates the characteristics of a laminar discharge pattern in an OR type room. And what they found is that the laminar piston of air kind of collapses on itself, highlighted by those orange arrows. And this occurs at a relatively low delta T for the space. So here we have the field collapsing at a delta T of 3.6 Fahrenheit. So that just means that the air coming out of the laminars is about 3.6 degrees cooler than the room air, which isn't a large delta T. So the fact that this coalescence or collapse occurs at low delta T's is a concern. The amount of collapse and acceleration is affected greatly by the temperature difference between the supply air temperature and the room air temperature. The collapse is also referred to as coalescence. The amount of collapse increases as the delta T of the cool supply air increases compared to the room ambient temp. One of the issues that this also creates is potential for entrainment of contaminated room air at higher delta T. This occurs when air outside the primary diffuser array is entrained into the laminar airflow pattern and then blown down towards the surgical table. This is a big concern in regard to infection prevention. So what can happen is you can see the airfield is collapsing here. And if you have contaminants that are flowing and cycling back up towards the ceiling, sometimes they can be pulled into this airstream. Because this is a relatively low velocity, but depending on the delta T, you'll actually create some acceleration here, and it can entrain some of those contaminants and pathogens back into the sterile field, flowing directly down on the OR table. So how can we prevent the collapse of the discharge airstream and also prevent potential entrainment of airborne contaminants? Well, the Krueger SteriFlow system, which integrates the air curtain with laminar flow, can help prevent those two basic issues. Air curtain systems help prevent two of the main challenges encountered with laminar diffusers alone. We still have the laminars placed above the surgical table, but we have to add an air curtain that wraps around the laminar flow diffusers. So here we have our SteriFlow air curtain wrapping around the laminar flow diffusers, which in this case are 5000 series laminar flow diffusers. So the air curtain is going to encircle the critical zone and discharge down vertically at a higher velocity than what we see from the laminar flow diffuser array. That higher velocity air curtain will create a second layer boundary to prevent any airborne contaminants from entraining into the critical zone. Instead, the contaminants should entrain into the air curtain discharge pattern and then be swept into one of the low-level return groups. So here you can see the SteriFlow air curtain system and wrapped around our laminar flow diffusers. And here we're actually showing some of our 5000 series with integrated LED lights. And you have optional blink off panels if you need access above the ceiling space. And the laminar flow diffusers in this image are laid into our framework's heavy-duty T-bar ceiling grid. As far as sizing the laminar array, the laminar array should provide about 30 to 40% of the total airflow into that space. The SteriFlow air curtain will then take up that remaining 60 to 70% of the total airflow. It's important to maintain those air balance relationships to ensure both the air curtain and laminar are acting the way they should. Each system is custom engineered to meet the needs of the application. Now in this illustration, we show multiple inlets, but you can receive as few as 2 inlets to feed the entire system. The plenum structure is linked on all 4 sides. These corner plenums connect each side so you can actually tap in from one end and the opposite end, and the air will flow uniformly around all 4 sides through the diffusers. It's also available in aluminum or stainless steel construction. Since the air curtain can handle higher velocities, 60 to 70% of the system, you typically don't need as many laminars to meet the total air changes per hour for the room space. This allows a reduction in the overall mechanical footprint needed to meet ASHRAE 170 space requirements. A smaller ceiling footprint should translate to easier integration with other ceiling equipment such as light fixtures, surgical booms, and gas drops. Basically, it's easier to get things through the ceiling if you don't have a laminar diffuser blocking its path. Finally, the air curtain also helps to eliminate the collapse of the laminar flow diffuser discharge pattern. Since the air curtain is a separate air pattern at a slightly higher velocity, it pulls out the laminar's discharge pattern, preventing the collapse of the laminar pattern. The laminar pattern comes straight down towards the table and exhibits little to no airfield collapse. The CFD illustration highlights those talking points. So you can see the air curtain is higher velocity, and the laminar flow is the lower velocity housed in the middle. So you can see that the laminar flow is actually flowing straight down, and the air curtain is helping to make sure that the laminar flow air is being pulled outwards. So it's not collapsing on itself, accelerating to the table. It's being smoothly pulled out and maintaining its smooth, uniform airspeed all the way down to the table. So we're making sure that we're getting that target 25 to 35 feet per minute velocity at the table. The air curtain helps to create a room within a room environment, which has been shown to be very effective at creating and maintaining a clean environment within the critical zone around the surgical table. Another thing I wanted to highlight on this illustration is that any of the airborne contaminants outside of the air curtain will swirl around in this space encounter the high velocity air curtain and be swept down towards the return. So the contaminants are not able to travel along the ceiling and entrain in the laminar flow diffuser. It's blocked by the air curtain. So the contaminants will always be pushed back down to the floor towards your low-level return grills. Now here we can see our Model 5000 series laminar flow diffusers. These are the ideal product to use for laminar flow discharge over an OR table. Now the 5000 series is available in aluminum or stainless steel construction. You can lay it in or surface mount it. So we've been focusing on kind of lay-in, but you can also surface mount these if you're working with a hard ceiling. It does include quick open fasteners and hanger tabs. The quarter turn fasteners are key for easy access for maintaining and cleaning in the OR space. It's also how you would access the HEPA filter housed in the unit for removing the HEPA filter and replacing it. Safety wires are included for each perforated face. So if the quarter turn fasteners come loose for whatever reason, the face will never drop down to the floor. It is attached to the plenum body using safety wires. You can house HEPA filters or OPAL filters inside the 5000, and optional integral LED lights are available. And in the illustration, you can see the LED light strips. And these are becoming more prevalent as OR room sizes increase. With larger rooms, you require more air changes. So 20 air changes in a larger room is going to require more air. So you begin to encounter issues where you may not have enough real estate in the ceiling to house all your light fixtures and air distribution and meet the 20 air change required by ASHRAE 170. So if you integrate some of those light fixtures directly into the diffusers, it should be easier when it comes to adhering to the ASHRAE standards and providing enough air changes per hour. Now, the Frameworks ceiling grid system provides a lay-in frame for laminar arrays, perimeter air curtains, surgical booms, access panels, and blank-off panels. It comes in fully customizable welded subsections. Basically, these are designed for each job. We start with a plan drawing of a surgical OR room, and we design the Frameworks grid based on the diffusers that are going to be placed in the space, the light fixtures, and any other structures that they might be encountering in the ceiling. So it is a fully customizable product. It's built into welded modular subsections to allow for easy installation in the field. There are 1.5-inch wide tees. They come with 8-inch thick gasket material provided for field installation. Blank-off panels are available, and they come in flat sheet metal, solid sheet metal, or perforated sheet metal with solid sheet metal on the back. So the perforated sheet metal is just an aesthetic option. It's not a true perf. You can't flow between the perf up into the plenum space. You always want your OR ceiling to be sealed. Here we have cross sections of the Framework ceiling grid, and you'll see on the left is a full beam section, and on the right is really what makes Framework's grid ceiling so unique and easy to install in the field. When you have multiple welded modular subsections that butt up to each other, they have a lock-align feature that allows the modules to basically snap together and create the look of a single full beam sectional. And now in the video, we'll show an example of how all these systems that we've been discussing can tie together for an OR room design. We do supply approval drawings for every Frameworks job that we do. Okay, so in summary, we review the ASHRAE 170 requirements. Diffuser coverage must extend 12 inches beyond the surgical table. This is defined as the critical zone, also the primary laminar supply array. 70% diffuser coverage must be provided over the critical zone. You must use non-aspirating laminar flow diffusers over the critical zone. Our goal is to provide 25 to 35 CFM per square foot of laminar diffuser phase to reach our proper laminar velocity. If providing filters with laminar diffusers, the filters must be equal to or greater than MERV 14. 20 air changes per hour are required, and of those 24 air changes per hour of some outdoor air are required. Laminar flow diffusers such as the Krueger-5000 are adequate for using above an OR surgical table. In addition, the Krueger SteriFlow air curtain can be used to encircle the laminar flow diffusers as an added barrier against contaminants. And finally, the Krueger Frameworks heavy-duty welded modular grid can be utilized to support the laminar flow diffusers as well as the SteriFlow. Now let's go into some design examples, and some of these are good and bad. Most of them are bad. So I'll let you kind of look at it for a second before I give you the answer, but some of these are going to be pretty obvious about what is not ASHRAE 170 compliant. So in this image, we see what's obvious, an OR space because of the equipment. And one of the things that kind of jumps out at you is if you look up in the ceiling, you have this swirl diffuser located right next to a light fixture. So we don't see any laminar flow diffusers anywhere. So the fact that they're using a high mixing swirl diffuser I would not consider this space to be ASHRAE 170 compliant. I also see return grills that look like they're high on the wall on each side. So we can't quite see the floor. So if they have low return grills on the floor, that's fine. But if this is the only location of return grills in a space, that is not ASHRAE 170 compliant. ASHRAE 170 dictates return grills to be low on the floor, 8 inches above the floor, ideally. So here we see another operating space. So what I see here is I see linear slot diffusers located and angling on the outer kind of transition to the ceiling. So these are linear slot diffusers, much like we provide in our GRD products. However, they are high mixing, and the way they're angled, it looks like they're discharging directly into the critical zone. And looking up at the ceiling, I do not see any laminar flow diffuser. So according to ASHRAE 170, this would not be compliant. So here we see another operating room space. And right away, we see up at the ceiling what looks to be, because we have a piping coming out of the wall, which is, this must be either VRF or some kind of fan coil. Either way, it's not ASHRAE 170 compliant. It's not a laminar flow diffuser. And, you know, honestly, anything that's involving the exchange of humidity and possible condensation sources within an operating space, that's going to be a potential source of pathogens. Okay, so now we're getting in some better examples. So here we see operating room space that has laminar flow, that has over adequate coverage for the actual table space. So we can see the laminar flow diffusers, they extend well beyond that 1 inch required by ASHRAE 170. And we see low mounted return grills. Now these look like they might be a little lower than 8 inches, but it's pretty good. The only thing I see are potentially just the level of the low return grills. ASHRAE doesn't want them to be too low because then you're just inviting, you know, easier pathway for the heavier contaminants, which would typically fall to the floor, to possibly be passed into the return grill. So that's why they recommend the 8 inch offset from the floor level. So here we see another good example, and this is also ASHRAE 170 compliant. We can see our laminar flow diffusers are located in the primary diffuser array directly above the operating room table. They've mounted a boom right in the middle. So you can kind of see why ASHRAE dictates 70% coverage for laminars and then leaves 30% for everything else, because you have penetrations of surgical booms that make it impossible to mount a laminar diffuser there. And here we see a return grill on the wall. It's kind of obstructed by the OR table, but generally this is a good layout. And finally, we finish off with a perfect layout, which is, of course, includes all the Krueger 5000 laminar diffusers, the sterile flow, and the Krueger Frameworks heavy-duty sealing grid. And we have our return grills mounted 8 inches above the floor in multiple locations. We have actually 4, but the 4th wall is hidden in this view. And we have our laminar diffuser array providing adequate coverage over the table. We've integrated the lights directly into the laminars, so we have full laminar coverage except for the 2 blank-off panels that must be located for the penetration of the surgical booms. So these surgical booms, they're not structurally supported by the framework grid or the blank-off panel. The blank-off panel just provides a penetration point for the surgical boom to enter the space. The surgical boom, that will be structurally attached to the slab or some kind of ceiling structure above. So now we're going to open up the floor for any questions that anybody might have, and I'm going to use Lily to help me out with that.
Yes, just as a reminder, to ask a question, just mouse over the bottom of the screen, and there you'll find the Q&A box. Just bring that up and ask your questions there. Neil, unfortunately on my side, I'm having some technical difficulties. I can't quite get to the controls here. So if you too want to bring up that Q&A in the chat and help read off those questions and help answer them, that would be appreciated.
You got it. Okay, so we have a question. Is the 25 to 35 feet per minute at the face, not the table? It's actually just at the table. There will be slightly higher velocity at the face of the laminar flow diffuser. Now, the perforation that we use is typically 13% free area for a standard laminar flow diffuser. So that applies a hard break. There is a high pressure drop. So laminar flow diffusers can't handle a large amount of air because they're intended to basically slow it down as quickly as possible. So the ASHRAE standard is for 25 to 35 feet per minute at the table. It actually doesn't dictate what the speed needs to be at the face. Okay, next question. Does ASHRAE 170 allow for less than 70% laminar coverage in the operating area if curtain system is used? No. You still need 70% laminar coverage, but what the air curtain will get you is that depending on how many air changes you need for the space, it could reduce the amount of laminar flow diffusers that you need. So you might have an easier time meeting that 70% requirement based on, the air changes if you're including the air curtain, because the air curtain can handle more air volume. As I was saying, 60 to 70% of the total air supplied for the system. So 30 to 40% would be handled by the laminars. 60 to 70% would be handled by the air curtain. So the air curtain is really there to create a buffer between the airborne contaminants outside of the operating space. And it also helps to provide enough air to meet your air changes per hour for some of the larger OR rooms that we're dealing with these days. Does the air curtain have an option for an integral MERV 14 filter? That would be a special. Typically, we do not have to filter the air curtain itself. Since the air curtain is intended to handle higher CFM loads, applying a filter device such as a MERV 14 or HEPA filter would restrict the amount of air that we could provide through the air curtain. So we typically do not have to address the filtering at the air curtain itself. Now, having said that, we can provide these with filters if needed. That's often not in the spec for when an air curtain is called for, but if it is ever needed, we can provide that. Is there a downside to oversizing the return grills? Not really. I would say the downside for undersizing is apparent, as in you would be dealing with noise and possible excess pressure in the space. Oversizing, as long as you're maintaining that 0.01 positive pressure in the space, that's all you have to be concerned with. So if you're oversizing the return grills to where you're achieving a negative pressure in the space, then you've gone too far. You have to maintain positive pressure, so you don't want any of those nasties to fly in under the door because you have negative pressure in the space. Positive pressure is required. So is airflow through the linear diffuser HEPA filter? Not typically. That's just the air curtain that we were touching on earlier. So if it is required, we can do it as a special. but 9 times out of 10, that won't come up. Do you have CFD analysis for how air moves under the blank-off panels? Not readily available. We're actually doing some CFD projects right now with our laminar flow diffusers and air curtain system. We have integrated some blank-off panels, so once we get the results, we'll have an idea of what those blank-off panels are exhibiting through that analysis. But that is currently underway, and unfortunately, CFD takes a lot of resources and a lot of time that we're currently sharing with some other projects. So we will be getting to it, and we should have something delivered by the middle of June. So we will be coming back to that. So Mark, I'll hopefully have some follow-up with you later. Does Krueger offer the air curtain separately for standalone applications? Yes, we can provide the air curtain for standalone application. It is a standalone system, so when you're pricing and looking at the SteriFlow, it is just the air curtain portion. It does not include the laminars. It does not include the grid. The 5000 provide the laminars, the frameworks provides the grid, and the SteriFlow provides the air curtain. Now, it's typically sold in a 4-sided configuration, but we can make single-sided, almost like a laminar, almost like a linear diffuser. I know some competitors provide that, so if that ever comes up, yes, we could do a 1-sided SteriFlow if you wanted to, or a 2-sided, or a 3-sided. So we see some ORs that actually have breaks in the air curtains. They have structure, or they have rails that something's going to be rolling back and forth. So sometimes you will see fewer than 4 sides on the air curtain, and we can accommodate those. We just cap off the plenum as needed, and those are custom designed as needed. So if you encounter those on a job, just reach out to us and we'll work through it. Is a factory startup required from Krueger, i.e. will Krueger send somebody out for balancing the system? Typically, this is not required. For these type of systems, a lot of balancers have a lot of experience setting up and balancing these types of systems. If you are looking for field support for balancing, we can definitely provide it. But as far as visiting the field, that's typically not required. What is the difference between HEPA and ULPA filters? So HEPA is an acronym for high efficiency, and ULPA is for ultra low. So ULPA is a next step up from a HEPA filter. So an ULPA would filter out 99.997% of particulates size at 0.3 or larger, where a HEPA filter filters out 99.97. So an ULPA is just the next level of filtration up from HEPA. HEPA is kind of the industry standard. And so you won't see ULPA called unless somebody is attempting to go beyond industry standard. And as far as ASHRAE is concerned, for the OR space, their highest filter efficiency rating is MERV 14. And a HEPA is already at MERV 17, so typically ULPAs are not going to be required to assure you're maintaining ASHRAE 170 compliance. If you're already providing a HEPA filter, you're already above and beyond what ASHRAE is asking me to do. Okay, here's another question. In what scenario could you get away without frameworks? So any type of scenario where you have a hard ceiling, which comes up from time to time, sometimes they're just going to surface mount laminars and directly above the OR table. And in that case, you could actually surface mount an air curtain or surface mount just laminars. If you just want to use the laminars, you could surface mount both the air curtains and the laminars. So in that case, you would not need a frameworks grid. Now, if they do not have a hard ceiling, you're going to need some type of grid. So if they don't have a hard ceiling, then they're going to need some type of heavy duty critical environment type of grid, which frameworks fills that void. Regular T-bar that you see in offices just do not cut it. There's too many leak points. But the great thing about frameworks is it is all aluminum extrusion. It is designed to be tightly integrated together, so you have as few cracks, seams, where you can have potential leakage from the ceiling to the plenum space. Let's see, is connection from the filter to the diffuser can leak? No, it should not leak. These are actually, a lot of times when they're setting up an OR room, they'll do leak testing with the filter installed in the laminar diffuser. We can provide laminars with aerosol injection manifolds to where they inject aerosol behind the filter and they wave a wand to detect how much of that aerosol has penetrated through the filter. And depending on how much of that penetration occurs, they'll pass or fail the unit. So no, it should not be leaking. The whole point of the HEPA diffuser is to have an airtight seal between the HEPA filter and the plenum chamber of that laminar flow diffuser device. Does the air curtain have individual balancing dampers for each diffuser to equalize airflow? Actually, we mount dampers in the inlets. So each inlet location can have a damper, but the actual diffuser itself does not really have an effective means to make manipulation to airflow. So the balancing is going to occur at the inlet location using an opposed blade damper. And I think that completes all open questions for now.
All right, so with that, enjoy the rest of your day, everyone. Thank you.
Thanks very much, everybody.